Thank you very much, Professor Sean. Today, I'm Dennis, first of all, and today we're going to be discussing the GraphMineSuite benchmarking suite. Essentially, what it's used for is both increasing the efficiency of certain graph mining algorithms as well as analyzing their performance, right? And the interesting thing here is that it does it by using Set Algebra and Set Algebraic Parallel Processing, a technique called SAP, which we'll see in a second here. So let's sort of dive in. Now, why are we even discussing this problem? Well, the motivation here is that, as a lot of the times we see, what we have right now isn't fast enough. So some of the current solutions that we see for graph analyzing, some of them are listed here. One's called Graph Challenge. Problem here is that with the current solutions for analyzing graph efficiency is that they're not very reliable or scalable, unfortunately. So they're a little bit weak when it comes to repeated axes, if you're a researcher or a computer scientist. So we need to find a way to get across that and find a better solution. Now, currently, we don't have a very good, that is to say, we don't have a good way of evaluating these graph mining performances that we see in certain graph mining problems and graphs. So we need to figure out a high-performant way. Now, the way to do that is going to be, as we kind of revealed on the title slide, it's going to be using the technique called Set Algebra manipulation to improve the efficiency and programmability. Okay, now the overview here is going to be, we're going to dive into some of the terms we need to understand some of what's going on with the paper and what exactly it's getting at. We're going to talk about the GraphMineSuite overview, so, sort of how it goes about what it does. We're going to talk about a couple use cases, just like the clique problem, as well as just a couple thoughts at the end. So, what is Set Algebra? It's in the title. Set Algebra is essentially what we've seen before in a class like 009, Fundamentals of Programming, right? So, the idea with Set Algebra is that, let's take, for example, in Python, we have the set structure here. Now, if we were to, a set has a couple of unique properties. It has, let's say, intersection, right? So if I had two sets, if I had a set with A, B, and then I intersected it with a set with just A, I would get out just A. Okay, so this is an example of an intersection property in sets. Now, there's also other properties, as we can see. Another one is union, where if we had the set A unioned with set B, what would happen is we would get an output set A, comma B, like so. And again, sets, the reason why we use sets at all in programming, as we know, right, some of these previous classes, is that sets are actually really, really efficient. So let's take, for example, if we were going to take a small problem like finding duplicates, let's say, and we used an array or a list. Well, what would happen is suddenly, if to check membership, for instance, it's O of n time. However, if we use a set, as GraphMineSuite does, we will end up with O1, constant time membership checking in this example with the finding duplicates problem. So that just goes to show how sets are really performant, they're efficient, and what sorts of properties we can do. There are other properties listed here, like the identity, complement, De Morgan's laws. These are also important, and these are all properties that GraphMineSuite takes advantage of in order to make the graph mining algorithms more efficient. So let's take another look at sort of what is graph mining altogether, right? Because here's another term that appears in the title of the paper. Now, the idea here is that when we have a graph like so, it can come in a whole bunch of different forms, right? It's not just maybe integers, but there's a lot of metadata associated with it, especially if it's a graph that is, let's say, a social network or some sort of medical distribution, recommendation system, and et cetera. there's a lot of metadata and extra data that we need to be able to query and sort of do some of these operations at a more complicated scale that we just talked about with the sets here. So that's why graph mining is a really big field in computer science, is because it's a very common data structure to help analyze some of the problems that we see today, as we see here. So there are already some techniques that we can use to analyze some of these graphs, such as pattern mining, clustering, classification. All of these are just tools that we currently use, just some examples of them that we use to analyze these graphs. Now, finally, we discussed that this SAP framework, or the Set Algebraic Parallel Processing Framework, is going to be the subroutine to GraphMineSuite, or GMS. And that's extremely the case, right? Because parallelism, as we've seen in a lot of different talks in this class, parallelism is the gold standard for improving efficiency for any algorithm. So we always want to reach for parallel processing, which the authors of the paper go ahead and do. And they sort of reveal their techniques there. Now, as we said before, it's indeed a subroutine of GraphMineSuite. And the important thing here, and we'll touch on this again in the concluding remarks, but what I found interesting was that GraphMineSuite is actually the first benchmarking suite for graph mining algorithms. Now that's pretty impressive. It's the very first one, and we'll discuss some thoughts about that in a bit here. Now, some properties of GraphMineSuite, the fact that it's using the SAP framework, it provides it with some properties. One is it's fast. We see some speed-ups of these modern graph mining algorithms that are presented in the paper mostly, of up to 9 times. That's pretty big. It's not, as Charles says, puny parallelism, right? I mean, this is pretty big. Now, we also see that we see flexibility when we use parallelism, and in fact, the SAP framework for GMS. We see that, in fact, we can use this technique for multiple different graph problems, not just, let's say, finding duplicates or just k-clique. We can extend and expand upon what we have, which makes it really flexible. We also have efficiency. Now, we talked about how set algebra is indeed very efficient and fast, and we see how that's used, and it provides a property. And finally, it's very scalable, and that was our original problem. Way in the beginning, we talked about how other solutions currently aren't able to handle scalability, right? When we have repeated accesses, when we have billions and billions of edges and nodes, right? So the GraphMineSuite is very scalable. Okay. Let's talk about some of the SAP framework properties. Now, we see some asymptotic bounds here. And we talk a lot about work and span in this class, and they're associated with time complexities. And here, of course, are some time complexities that we see in the paper. Now, let's analyze the k-clique listing with node parallels. It's the one, the leftmost analysis. And we see that it has this work of mkd over 2 to the k minus 2. Now, at first I read this and I said, okay, what does that mean? It's nothing I've ever seen before. But then I compared it with a competitor, which actually came about a month after, funny enough, with one of the same authors, Besta. And what was interesting is that this new algorithm, as far as I can tell, runs a smidge faster than the one that this paper provides, which is interesting, right? It really goes to show how, as the times go on, we see a lot of improvements, even in these niche subjects like graph mining, right? And I think we can see where exactly the improvement comes from. It seems that there's this extra k term here in the current GMS paper, but in this competitor's paper, we don't have that k term, right? So that seems to be pretty interesting. Yeah, over there.
Do you know what alpha is like defined as or represents?
Yeah, that's a great question. So the question is, what is alpha? What does it represent? Oftentimes, alpha is used, especially in signal processing, for instance, as sort of the peak of the magnitude of, let's say, the phase transform. In this case, I would imagine it's more of how many of some item fits in each block in one of the subroutines. So there are definitely different aspects of what alpha could be.
Yeah. So I think alpha is the arboricity of the graph. It's a measure of the sparsity. So it's within a constant factor of d, which is the graph degeneracy. Yeah. So like you can think of d and alpha to be on the same thing, at least asymptotically. So you're right. Like you do say the factor of k on the, I guess, in the compared to the work over at the top.
Right. Yeah, so that is really interesting with the arboricity and the graph denseness. And it's funny that we mentioned that because graph denseness also comes up in a later point that we'll hit here. So that's pretty interesting. Now, there's also another problem that GraphMineSuite is really good for, and this problem is called subgraph isomorphism. But what is that exactly? So essentially, it's this problem in graph theory where you have, essentially, you want to prove an injection between two different graphs. So here's a good example of an injection that came from a professor of the class I'm taking called 6045, Computability and Complexity Theory with Professor Rubenfeld. And I really like the way she described it just the other day. So essentially, an injection is where you have two graphs, and one of them, so let's call this A and let's call this B. So they each have some number of elements. Let's put 3, but it's unknown to anybody else that they both have 3. So the way that we prove that they both have indeed 3 elements, or the same number of elements in general, would be we take each element in A and we simply draw an arrow to the other corresponding element in B. And we do that for every single element here. And if there are no elements left to draw arrows to or from, well then we've proven an injection between the two graphs A and B. Now this is really big. A lot of computer scientists strive to prove such an injection and other things involving sets like bijections in order to prove certain properties and essentially make their graphs much more efficient and their algorithms more efficient. So anyways, injections are, again, the cusp of essentially the main idea of subgraph isomorphism. And here's a more formal definition of what we sort of drew here. But how does GMS exactly use subgraph isomorphism? So we can go back to a point that was told to us earlier in the term. In fact, it was lecture 4, and it was regarding Silk's work-stealing process, which I thought was really interesting. I'm sure all of you did too. But the idea here is that GMS sort of takes this Silk, or not specifically Silk, but this work-stealing process that we've seen in Silk, and it combines it with subgraph isomorphism, which we demonstrated earlier, and essentially it yields a performance increase of about 2.5 times, which is, again, non-trivial. And if we recall here, the work-stealing algorithm was also very interesting. The main idea was that we have a couple of DQs or decks like so, and then the current main process takes from the bottom while another thief, as it's called, steals from the top. And in that way, we can achieve higher parallelism. So that's pretty interesting that we achieved this performance increase using GMS and work stealing. And in fact, here's a good example from the paper itself where we have this plot here. In fact, the purple one is going to be the baseline for this VF3 light parallel algorithm, which is found in another paper. I might have listed it here. If not, no worries, but it's online. And in fact, we also have its comparisons. Now the kicker here is that the green and the red, which represent sort of this work stealing process, which we were talking about before, specifically as it relates to GMS, we see that critically these are much below the baseline, which is what the VF3 light parallel was using beforehand. So this is pretty interesting, and it's a good visualization of how GMS sort of achieves this performance increase by using the subgraph isomorphism that we were talking about, as well as the work stealing, similar to how Silk does it. So another problem we were discussing in this graph and in the research that went into this, we have another problem called the Four-clique problem. Now, this is another popular graph problem that can be improved by the GMS benchmarking suite here. Now, but what exactly, let's get a refresher on the Four-clique problem. So essentially, it's where you have a graph, and when you have nodes that are densely connected, and sort of essentially when you have clusters of nodes, oftentimes you'll come up with these cliques, which are essentially in this four-clique example, 4 nodes that are all connected to each other. Which we see a few examples here on the right. Now, if we had a 2-clique like so, we would have just 2 nodes and 1 line. Of course, it satisfies the property that all nodes in the clique are connected to each other, but it gets more complicated as we see when we go to the 3-clique and then yet the 4-clique and so on. So this is a little bit of a context and a background to what the clique is. Again, essentially it's a subset of the nodes that are connected to everybody else in the graph. Now, why is this important? Well, as it turns out, there's this use case in the paper that was discussed. And the use case was with a couple companies that we may have heard of before, Flickr and this other one, LiveMocha. So Flickr, just for context, as we know, is this photo sharing network. And LiveMocha is a little more obscure, but essentially it's a language tutor matching app. So we have these 2 apps in these different fields, but why is that important in this use case? Well, the authors were actually pretty perplexed about the outcome of GMS's analyzing of these 2. In fact, given that they both have the same number of edges, the same number of nodes, and a relatively the same density, well, as it turns out, there happen to be much more 4 cliques in the former, in Flickr, than there were in LiveMocha. Yeah, so that's really interesting because, again, at face value, they seem to have the same sort of characteristics, but when we analyzed it with GraphMineSuite, we found that the number of 4 cliques is, orders of magnitude larger than the other one. So why could this be, right? Well, we think that, and especially the authors think that, this has to do with the characteristics of the graphs. And again, in the beginning of the talk, we discussed how there can be different types of graphs, like public transportation, medicine, social networks, right? So we see that really come into play here because, as it turns out, Flickr, by nature being more of a photo-sharing social network, it has a lot more metadata that's associated with the nodes involved, right? So for instance, we have location, we have tags, right? Who's in my photo, the title, and so on, right? But as it comes to LiveMocha, as it turns out, we don't have as many of these overlapping characteristics. In fact, LiveMocha seems to only be limited to language skill, proficiency levels, and learning goals. So the point is fewer characteristics, which sort of led to this lack of four-cliques that we saw. Not the lack, but the significant decrease, as opposed to Flickr, which is kind of interesting. And this outcome, this sort of characteristic, was found via the GraphMineSuite analyses that the authors performed. So that's an interesting use case. Now, finally, we're going to discuss a little bit of a trade-off between using GraphMineSuite and some of its competitors. Now, as we see in the paper, the authors sort of discussed this sort of work and space time complexities that we see in a naive algorithm regarding some sort of searching. It was this unnamed searching algorithm. Now, as we see here, the naive implementation is as theta n delta to the k minus 1 for both the work and the span and the space. Now, the funny thing is that when we went and we used GraphMineSuite and the SAP framework, which we sort of discussed before, when we went and we used that, it turns out that what we sort of wanted and a performance increase, right? So we like that the work sort of decreased, but what's funny is that the space increased, which is not something we want. So this really goes to show how we have some sort of a trade-off between the benefits and the drawbacks of using GraphMineSuite and some of its analyses, right? Now, just to close off, let's discuss what we talked about. So we sort of overviewed GraphMineSuite, what it uses as subroutines, so set algebra, set algebraic, performance enhancement with the SAP framework. We talked about GMS, some of its use cases, right? We talked about the cliques problem, different types of graphs, different solutions it uncovered. So just a couple of my thoughts here. I thought that it was interesting that GraphMineSuite was able to increase the performance of some of these algorithms up to 9 times in some cases, probably even more. However, it's it's self-admittedly the first of its kind, right? So as it turns out, in their conclusion, they said that GraphMineSuite is the first extensive graph benchmarking system suite that we see. And the thought that came to me was, well, I saw this article the other day regarding Apple's new iOS 17 release, which is rumored to come out this upcoming WWDC. Now, the problem is, well, iOS 17, huge leap in software engineering, but it's leaving behind a lot of these first adopter technologies like the iPhone 10, for instance, the first iPhone with no home button. So the point here is that when you're the first of your kind, well, sometimes you get left behind, right? And in fact, we've already seen that when we talked about the work and the span asymptotic analyses. In an earlier slide, we sort of touched on the fact that this other paper, a month after this paper here on GraphMineSuite, came up with a slightly better bound in the span of 1 month. So I think those are my thoughts regarding this, and thank you very much for listening. Do you have any questions? Yeah.
I'm just curious about, because I don't think the paper really elaborated on, is there a difference between graph mining algorithms specifically and just like general graph computations?
Yeah, that's a really good question. So the question is, what makes graph mining so special as it relates to sort of graph analyses in general? Yeah, I think that's a good question. We can kind of discuss how in earlier classes, like in one of the prerequisites to this class, 006, well, we see that a lot of the problems involve very simple things like, I don't know, some sort of DFS between here and here, or some sort of Dijkstra, and we're using sort of these simple like integers, let's say, and it doesn't get more complicated than that. But when it comes to graph mining often has the characteristics that we talked before about. For instance, the medical distribution, we have public transportation, we have the Flickr, right, photo sharing network. The point being that, as I understand it, graph mining is unique in that it hosts more complicated ideas and more metadata and more complicated structures of data within its graphs. So I hope that sort of answers your question. Do you guys have any more questions? No?
I just wanted to elaborate on that. So a lot of subgraph mining algorithms leverage set operations, like set intersection. If you want to find triangles, you take two neighboring vertices and you take the intersection of their adjacency list. So that's the number of triangles that you have. Whereas simpler things like breadth first search or depth first search, they don't really use these set operations. They're mostly just like doing simple operations to traverse the neighbors, as Dennis said. So.
Yeah, that's a great explanation. Thank you very much, Professor Sean. All right, well, I guess off to the next presentation.